Alright, it's time to interrupt my uploads of Dyson Sphere program with another Math Nerd video! Why? No, that's the wrong question. It's why not? Math is fun and amazing! And today I want to talk about something that will help you with division, not cellular division. So, don't get your hopes up. But there is a well-known trick that if you want to see if a number is divisible by 9, you can simply add up all the digits of the number and see if that result is divisible by 9. And if the result is, then you know the first number you started with is also divisible by 9. So let me give just a couple of examples to show what I mean by that. We'll start off really simple. The first number that's not 9 that's divisible by 9 is 18. It's pretty obvious that 18 is just 9 times 2. But look at the digits of 18. It's a 1 and an 8. And what is 1 plus 8? You've got it, 9! Same thing with 27. 2 plus 7 is 9. And 27 is divisible by 9 as well. In fact, you can just make up numbers and automatically know that they are divisible by 9 as long as you add the digits correctly. So let's give some semi-random digits. 5, 2, 1, 0, and let's throw another one in there. Why? Because that will make it add up to 9. That's why. That's the only reason why. That's why I picked the numbers that I did, because I wanted it to add up to 9. So 52101, that's 52,101. And you can find out very quickly using a calculator that 52,101 divided by 9 is 5,789. While this is not the point of my current video, if you want to know a quick trick to how to divide numbers by 9, let's look at this 52101 again. And look at the answer we got, 5789. Do you notice a pattern with the way that that first number becomes the second number? Well, notice, first both numbers begin with a 5. But what about that second number in the sequence? In 52101, the second number is a 2. That's why I emphasized it there. And in 5789, the second number is a 7. What's the relationship between 2 and 7? Well, obviously the difference between them is 5, and 5 was our first number. Is that just a coincidence? Or is there something else going on? Well, what about the next number? In 52101, the third number is 1. In our answer of 5789, the third number is 8. And what's the relationship there? Well, 8 is 7 more than 1. So do you see the pattern yet? If you think you do, the next bit may cause a tiny bit of confusion. After all, in our original number, the next digit is 0, but in our answer, the final digit is 9. How does that fit into the pattern that you may or may not be seeing yet? Well, it doesn't directly, but when you consider the final digit of the original number is a 1, and 8 plus 1 is 9, and then if you also remember that there is one fewer digit in the answer than there was in the original number, then you might actually figure out why it makes sense what it's doing. But let me explain all better. So far what I'm saying is kind of complicated. But consider first dividing by 10 instead of 9. When you divide by 10, it's very, very easy, isn't it? If I asked you, clear out of the blue, what is 9,381 divided by 10, you would instantly be able to say it's 938.1. Why? Because all you do is move the decimal point over. 9381 is really 9381.000000 forever, with an infinite number of those zeros afterwards. And if you move the decimal point one place to the left, which you do when you divide by 10, 9381.000000 becomes 938.1000000. And we ignore all those repeating zeros, but we need to emphasize them here just to make my point. Anyway, that's an aside. When you think about it, though, 9 is very close to 10. It's only 1 away from 10. So when we look at our first number that we had, 52,101, and we divide it by 9, we can think of it as beginning roughly the same way as if we were dividing by 10. You can simply move a decimal point over 1. So in your mind, 52101 becomes 5210.1. Now, that obviously doesn't get us very far, so when you're doing this division, it's not really worth writing that number out. But what it does do is it means that our first number is going to probably stay the same each time. And so we'll be one order of magnitude less than the original number that we're dividing, but that should be expected. In other words, dividing a number in the 50,000s by 9 will have an answer in the 5,000s. You can roughly bet on that. There may be some exceptions, but most of the time it's going to be that simple. But we still need to calculate the other numbers to get them to show up correctly. So again, let's look at that first 52,101. We know that the answer is probably going to begin with a 5, so write down 5 first. Now the next number in 52101 is that 2. Simply add the 5 from our answer to the 2 in that second digit to get 7. Now we have an answer that we say is going to begin with 57. And we just repeat that process we just did. The next number in the original number is 1, so we add 1 to our 7 and write down 8. 578. Next up we have a 0. Well, 8 plus 0 is just 8 again, so we would write down 8, and we'd have 5788. But now we have our last number, which is another 1. 8 plus 1 is 9. But since we're dividing by 9, we just carry that 1 to the previous number. This is exactly the same process as when you're carrying 1 when you divide by 10s, but here we're doing it with 9s instead of 10s. So if we carry that 1, that means our final 8 has to increase by 1, and we end up with 5789 as our final answer. Now that you know that, let's look at this 52,101 again. We know that all of these digits add up to 9, but if you rearrange them, whatever order you pick those digits to be in will also add up to 9 because the digits are the same. And just rearranging digits is going to add up to the same result for the digits. The new number that we get will also be divisible by 9 if the theory that all numbers divisible by 9 add up to 9 is correct. So let's just rearrange this and say, look at the number 11025. That's going to be our new number. Let's divide that by 9 to prove it is divisible by 9. Let's use our new math technique too. So again, the answer will start with 1 because it began with 1. Then we have 1 plus 1, and that gives us 2. So we'll have 1, 2. 2 plus 0 is another 2, so we just write down 1, 2, 2. Then 2 plus 2 is 4, so we have 1, 2, 2, 4. And finally, 4 plus 5 is 9. So we carry the 1, and we get 1, 2, 2, 5. Now you can multiply 1225, that's 1,225, by 9, and you see that it does indeed give you 11,025. So this is working. Now you might wonder how to do this division trick when the 9 happens earlier rather than at the last digit. So far all the examples happened at the very end. So let's look again at a new number. Let's try 54702. The digits here add up to 18, and of course 18 adds back up to 9, so we know it's divisible by 9 again. So how do we do our division trick here? Well, we start again, we write down our 5, then 5 plus 4 is 9. So we carry the 1 and change that to 6. So we're actually now beginning with a 6. This is why it's not a guarantee that the number that you start with will always be the same one. As I showed right here, we've had to increase by 1 to make it start with a 6. But while we increase that number by 6, we can't forget that carrying the 1, we have to change the number that follows it to a 0. We have to keep that 0 because that 0, which was a 9, increased the number that was to the left, but it still exists as a place. So we don't have 6 to start with, we have 6, 0 to start with. And now we continue. 0 plus 7 is 7. So we write that down next. So we have 6, 0, 7. 7 plus 0 again is 7, so 6, 0, 7, 7. And finally we add the 7 plus 2 to get another 9, which we then carry over to make our final answer 6, 0, 7, 8. Anyway, that was all a bit of a side and it has nothing to do with the point of this video, so let's get back to the point. Why is it that the numbers that are divisible by 9 have digits that sum together to be a multiple of 9 as well? That is the question this video is really about. So, to answer that, let's consider a different way to write digits. We'll keep it simple and just look at 18 for our example for now. What is another way to write 18? 18 is the same thing as 8 times 1 plus 10 times 1. That is to say that 8 is in our units value and 1 is in our tens value. And we can demonstrate that by thinking of a variable. Let's call it d for digits. It's going to be a series of digits, so we'll use an index number, which is going to be a sub number below the d. That's just an index. It has nothing to do with any mathematical functions or anything. It's just to reference the position of the digits, so keep that in mind. So now we have a number. We'll say the number is n. and it's represented as follows. N equals D0 times 10 to the 0 power plus D1 times 10 to the first power plus D2 times 10 to the second power, and so on, up to some arbitrary number, let's call it M, dm times 10 to the m power. Okay, the subnumber used for the index is going to always be the same as the exponent that we're giving to our 10. When we do 10 to the power, it's going to be the same as the index. And we'll make that m our maximum index value. We can make that be whatever we want it to be. It can be arbitrarily large. So doing this, we can represent any number we want. Remember, 18, for example, is the same as if we just described D0 equals 8 and D1 equals 1. That's the same thing as writing 8 times 10 to the 0 power plus 1 times 10 to the first power. And remember, any number to the 0 power is going to be 1. So 10 to the 0 power equals 1. So 8 times 10 to the 0 power is the same thing as 8 times 1. So just bear that in mind. So now we have our new way of representing normal values of numbers. We can use this to represent the sum of digits in the same way. Using that same d variable, the sum of digits would just simply be like this. We'll use s for sum. S equals D0 plus D1 plus D2 plus all the other numbers up to Dm. So again, the digits in 18 would be the same thing as saying D0 equals 8 and D1 equals 1. And if you're going to add all those D's together, well, clearly D0 plus D1 is the same thing as 8 plus 1, and that gives us 9. And 8 plus 1, remember, you kind of have to reverse it in your head, but that is our 18, because the 0 goes first in this depiction. So now that we can represent the digits of a number using our D indexes, and we can represent the sum of the digits in that same framework, let's just consider what happens if we subtract s from n. In other words, our n is the number that we're representing, the s is the sum of the digits. If we subtract them, we have n minus s equals D0 times 10 to the 0 minus the D0 of the digit itself. Then we're going to add in D1 times 10 to the first minus D1 itself, plus D2 times 10 to the second power minus D2, and so on, up to Dm times 10 to the m minus Dm. And yes, that looks complicated, but notice something here. First, D0 times 10 to the 0 minus D0 gives us, since 10 to the 0 equals 1, that's the same thing as saying D0 minus D0, which is 0. So we can just ignore that one completely. Just remove D0 from our equation. Second, D1 times 10 to the first power minus D1. Well, since 10 to the first power equals 10, this is the same thing as saying we have 10 lots of D1 minus D1. Well, that's the same thing as just saying 10x minus x, and that gives us 9x. So this is the same thing as having 9 D1s. Do you see where I'm going with that? Next up, D2 is 10 to the second power minus D2. And since 10 to the second power equals 100, that means we have 100 D2 minus 1 D2 means we have left over 99 D2. Now, that's somewhat complicated to say, but basically, if we are subtracting our sum of digits from the regular amount that we started with, the result that we have left over has every single existing value a multiple of 9. The first one is 9, the second is 99, the next one is 999, and so on. And perhaps an example will help show this more clearly. Using 18 once again, we have the following. Remember, D0 equals 8, D1 equals 1. D0 times 10 to the 0 power minus D0 equals 0. And D0 equals 8. We've just plugged those in. Well, 8 times 10 to the first minus 8 is the same thing as 8 times 1 minus 8, or 8 minus 8, which equals 0. So that part checks out. When we continue with the second number, D1 times 10 to the first power minus D1 equals 9 D1s. Remember, D1 equals 1. So 1 times 10 to the first minus 1 equals 9 times 1. 1 times 10 minus 1 equals 9. And 10 minus 1 does indeed equal 9, so that part checks out as well. But that's really simple. Let's use a bigger number. Let's use 351, because we know that that adds up to 9 as well. In that case, we have this. The D0 is going to be the 1, D1 will be 5, and D2 will be 3. So once again, D0 is going to cancel out and make us 0. That's the same thing as D0 times 10 to the 0 minus D0 is, in this case, 1 times 10 to the 0 minus 1, or 1 minus 1 equals 0. So again, that cancels out. That does exactly what we expect it to do. d1 times 10 to the first minus d1 is going to equal 9 times d1. And d1 in this case equals 5. So we substitute that in. We're saying 5 times 10 to the first minus 5 is going to equal 9 times 5. Well, 5 times 10 to the first is 50, and we're subtracting 5. That gives us 45. 45 is indeed what 9 times 5 is, so again, that checks out. Now we throw in d2 times 10 squared minus d2, which is going to equal 99 lots of d2. So our number here is 3. We sub that in. 3 times 10 to the second is 300 minus 3 is going to equal 99 times 3. Well, 300 minus 3 is 297, and 99 times 3 is 297. So now we've established that n minus s will always be some value which is a multiple of 9. So we can write that as n minus s equals 9x. Multiplying the x here by 9 guarantees that whatever is on the right-hand side of this equation is divisible by 9. But notice something peculiar here. This is true for all numbers, not just those numbers that are divisible by 9 to begin with. Consider the number 22, for example. If we add up the digits of 22, we get 4. That's 2 plus 2 equals 4. And 22 minus 4 is 18. 18, as you recall, is divisible by 9. Or let's take 1347132. I just randomly mashed those keys down when I was writing my script for this. 1347132 added together gives us 21. And 1347132 is the same thing as 1,347,132. Subtract 21 from 1,347,132, and the answer is 1,347,111. Now, using our new division technique or a calculator, it's your choice. We live in the 21st century. I won't judge you. You can easily verify that 1,347,111 divided by 9 equals 149,679. Okay, so that's all great and fun, and it's interesting on its own. But again, this video claims to show why any number that is divisible by 9 has digits that add up to 9. All I've proven so far is that if you subtract the sum of a number's digits from the number itself, that answer is always divisible by 9. After all, 22, which we looked at earlier, is clearly not divisible by 9, and yet it follows the same rule we just established. So what's the point? Does anything that I just said even matter? Well, let's return to the equation that we've come up with so far. N minus s equals 9x. We've seen that this is true for all values no matter what. But we want to know specifically when n is divisible by 9, what must s be? So just as we can guarantee that a number on the right-hand side of the equation is always divisible by 9 because we're multiplying our x by 9, let's represent n by using another variable to guarantee that what we're looking at when we're considering values of n that must be divisible by 9. To do that, let's say that n equals 9m, and it must be integers. We are not dealing with fractions in our ideas here. So we're only considering the n's that are of the pattern 9m when we're thinking about this. So we'll do it this way so we can still keep our n in our current equation, but n will always be divisible by 9 in our minds. So just bear that in mind. So now we have n equals 9m and n minus s equals 9x. That's the same thing as saying 9m minus s equals 9x. Now, if this is true, and it has to be true, that 9m and 9x are both divisible by 9, then necessarily it must follow that s is divisible by 9 as well. After all, if s is not divisible by 9, then subtracting s from 9m would result in an x value that is not divisible by 9. Think of it this way. If we start off with m lots of 9, and we subtract some value of s, and we end up with x lots of 9, then the value that we subtracted had to be a value of some number of 9s. But we can also do our equations here. If we rewrite this equation just using regular algebra, we can rewrite this in terms of s as follows. First, subtract 9m from both sides, and you get negative s equals 9x minus 9m. Then you can just multiply both sides by negative 1 to make s positive, and you get s equals 9m minus 9x. We can now factor the 9 out on the right-hand side and get s equals 9 factored out of m minus x. We can then substitute m minus x with a new variable. We'll just call it y for now. Just say y equals m minus x, and now we have s equals 9y. But this means s is 9 times this other variable, and so s is divisible by 9. And by that same reasoning, if we stipulate that s is the number that's divisible by 9, then our original n must be divisible by 9 too. It's the same exact logic. So in other words, if the sum of the digits of a number is divisible by 9, then the number itself must also be divisible by 9, and vice versa. Therefore, we have proven that every number divisible by 9 must have the sum of its digits also be divisible by 9. So this, finally, is the reason why any number with digits that adds up to a multiple of 9 must be divisible by 9. And there you go. Now, not only do you have a nifty little trick to test whether a number is divisible by 9, but you know why it's divisible by 9 and why it must be divisible by 9 if those digits add up to 9. So there you go. I hope you all have a wonderful day, and peace out.